like right. You probably just scream for a while.
Okay. Okay, today we're going to start the ultimate topic. Random variable generation was the penultimate. This is the pencil ultimate or something. Okay, we've been spending the quarter building these particular types of simulation models, these discrete event models. We have a methodology for doing so. We have a means of implementing them. And we have a means of testing them. And now, what the heck are they telling us? The thing is that building models of any kind, including simulation models, is not a useful activity in and of itself. In other words, you could, if you build the most wonderful model in the world, and that's all it does, then you've had some fun and done something creative maybe, but not really useful. At the end of the day, if there isn't something that you know that you didn't know before, then there was no value added. So you might ask, okay, now why the heck are we doing this? That's the topic that we're going to talk about for a little bit, and we only have enough time to kind of dip our toes in it, because this is a whole subject in itself. There is a course on this over in operations research that used to be somewhat in the matrix, but then when it was kind of Honey, I Shrunk the curriculum, it got sent overboard. So that's where output analysis is. Okay, now that we have the model, what the heck is it telling us? And again, why do any of this stuff in the first place? Why have a discrete event simulation model when there are other possibilities? Generally, when what you're dealing with has randomness in it and dynamic things. In other words, dynamicism and randomness are two of the qualities of a system you're trying to study that will often lead to a model such as the one that we've been talking about all quarter. Why? Because there are situations where you can write down an equation or maybe apply a particular algorithm to find your answer. And in those cases, generally, the kind of if there's randomness involved, and then particularly if there's dynamic things happening, the kinds of assumptions that you have to make in order to write down these equations or apply a particular algorithm are generally far too restrictive for the kind of system you're studying. In other words, once you kind of break those assumptions, then you're kind of out in the wilderness. That's why this even exists. And in your statistics classes, you've acquired tools for studying these types of, or some types of random systems. In other words, if I gave you a data set which consisted of a random sample, you remember how your stats class defined a random sample? Or they use that term, I hope? Yeah. Basically, if you have these IID things and you want to know something about it, such as what is the average, what is the mean of this collection, you have tools to do that. And those are the kind of tools we want to try to apply. But we're immediately kind of led to some issues with the kind of data that these simulations produce. And that leads to, and there are also kind of two somewhat different situations, because these are dynamic systems. And when you look at dynamic systems, there are issues that start to come up, and we'll start to look at that. One of the bifurcations in terms of how you're approaching studying it is whether the simulation is a terminating or a non-terminating. And I'll go into more detail about what that's about. But briefly, well, there's a little bit of, in a sense, all simulations are, quote, terminating in the sense that they have to terminate in order for you to analyze them. In other words, if it runs forever, you're never going to get an answer. So there's a special meaning of what that is. Namely, in a terminating case, there's a natural end state for the simulation, whereas for a non-terminating, you're typically interested in more long-run measures. And so of the many types of analyses that we could do in our remaining time, we have only enough time to really look at the objective of finding a confidence interval for specific measures, first for a terminating simulation, and then for a non-terminating situation. Each of those have things that come up. And particularly for the terminating is actually the easiest to implement. But when you kind of delve into what the heck it is you're doing, it becomes a little bit complicated. And that gets back to this notion of a random sample. If you remember, the assumption of a random sample, as you said, was independent and identically distributed. And so we'll see how we can get independent and identically distributed values. In other words, how can we get a random sample so that we can apply all those wonderful things that you acquired in your statistics class, or sadistics as some call it.
You're a roll day.
I'll be here all week. Okay, so our objective is to learn something about the system being modeled. In other words, that's the purpose of this whole thing. Like for the models that I'm working on for NevSup, it's because they want to know things. And so they could care less about any model that I or anybody else could create for them, except as it gives them answers that they want. Now, as I said, the application of a discrete event simulation is typically in a stochastic setting, which is a fancy word for random. I just like saying stochastic because it's cooler than random. And as I've talked about a number of times before, we've been running our models once, and that's not something that you can really take to the bank, because it's akin, again, to flipping a coin once and trying to estimate the probability of heads. Running a stochastic model once, you have no idea how representative that value you got was. Was it close to what you would expect? Was it an outlier? Did you get lucky or did you get unlucky? You just simply don't know. So of the models that we've looked at, really the canonical, one of the canonical measures is the delay in queue, or the waiting time. You know, how long do customers spend in the queue? We're going to kind of treat that as the canonical one, but there are lots of others. As we've seen, we have things like time in the system, number in the queue, utilization, average number of busy servers, available servers, etc. In models like our reneging case, well, what was the average percentage of lost customers that we had due to reneging? How long, what was the average time to process a job in cases where, like with the ships? I mean, how long did ships stay in the queue? What was, given that the processing times were different Could potentially be different depending on how many cranes were operating on them. You know, how long did it take to process? Or how long did it take to just kind of finish everything and get out? There are other, you know, like one of the main measures that they were interested in was something called fill rate. So what's fill rate? Fill rate is when you need a replacement part, do you get one right away? Yes or no? And if you do, then that's a 1, and if you don't, that's a 0. So the rate is basically the probability that if I need a part, I'll be able to just get one right away. Very simple measure, but a very important one, because that ties directly into, you know, things like availability. In other words, if my system is down for, for want of a horse or for want of a shoe and all that, if the system is down because of this part, and I don't get the part no matter how, no matter how, seemingly unimportant the part may be, if the system doesn't work because of it not being there, and you can't get one because they're all out, then the system is down, and that affects availability. And availability and readiness are things that they're very interested in. Okay, so for any given model, there are going to be a number of different measures that the model is capable of producing. Now, what you should have a sense of by now is that every measure, in these discrete event models, there are things which don't change, and those we called parameters, and there are things that do change. We've called those state variables. So the only things that change are state variables, and therefore any measure that your model could possibly give you must be some function of the state trajectory of some state, or of all states. Okay, so we're going to focus on just one measure, and if we have more than one measure, we could apply it to whatever ones that we want. Okay. We agree that a single replication is not sufficient. And now we're going to talk mostly about the mean, but understand that that's not the only thing that we might be interested in. We might be interested in the maximum. We might be interested in the standard deviation. We might be interested in a quantile. There are lots of different things, and again, in our time, we're going to just focus on means and just understand that's not the only thing. So now, let's assume somehow we have our random sample. Again, we're back in our stats orientation. And I want to estimate the mean of a random sample. So how would you do it?
Take a ton of samples and average them?
Yeah, take a bunch of samples and take the average. Now, so we take some samples and we get the average. So in a way, we're doing better than our one flip, but how accurate is that average?
Depends on how big the sample was. It'll approach the true population mean as the sample size increases.
That's true. So how do you know whether your sample size was big enough?
The t-score being sufficient for whatever confidence interval you're trying to.
You said the magic word, confidence interval. In other words, just estimating the mean in itself is still not completely sufficient because, again, it gives you don't know whether you've taken enough samples. And if you have a situation where the variance is very, very large, even taking a lot of samples doesn't necessarily guarantee that your estimate of the mean is accurate, and that's where confidence intervals come in. So you know what confidence intervals are? And they hopefully talked about what a confidence interval means.
Spoken about it a lot. We get 3/4 of
We've done a lot
statistics.
of confidence.
A lot, okay, yeah. All right. So you have a lot of confidence in how confidence interval about. Okay. All right, so that's the bare minimum of what we need. Okay, so this is all review. So if we have a random sample, that is if they're independent and identically distributed, then we have a point estimator for our mean is the sample mean. So you understand the difference between this unknown true mean of whatever our system is and our estimate of the mean, which is our sample mean, sample average. Now, we also don't know what the variance is. And actually, if depending on how mean your prob guy was or your stats person, they may have mentioned situations where the variance doesn't exist. They probably didn't talk about that. That's okay. But there are situations where the variance actually doesn't exist. Does not exist. Or is infinite, or however there are. In fact, actually there are there are distributions you've encountered that actually do that. If you remember the t distribution. Okay, the t distribution with 1 degree of freedom has no variance. It actually doesn't even have a mean. But again, especially if we're doing confidence intervals, we're never in a situation where we're only taking like one sample. So that's just an FYI. Okay, so if we have a random sample, then our estimator of the variance is the sample variance, which is this funky thing, which you're probably all familiar with. And I don't know. In this day and age, it's okay. How do you find the mean? Well, you put it into the software, and it'll tell you the mean. How do you find the variance? You put it in the software and ask for the mean. It'll tell you that. And so we don't need no stinking equations. So now here's the thing. Okay, what additional assumption was made to say that our confidence interval is the sample mean plus or minus our estimate of the standard deviation over root n times this t quantile?
It's a two-tailed interval.
Yeah, this is the student t distribution. But there's one additional assumption that has to be made for this to be valid. Do you remember what that is?
Residuals are normally distributed.
Exactly. In other words, the assumption is that our random sample is independent, identically distributed, and normal. Now, consider our canonical measure, which is delay in Q. Is it possible that the delay in Q is a normal random variable? Okay, so what makes you think that? So if I measure the delay in Q, could that possibly be normal?
I don't see why.
What-
I don't see why not.
Why not? Well, what is the range of values of a normal distribution?
0 to
How are you parameterizing it?
Doesn't matter. For a normal distribution, is it possible to get negative values? For the delay in Q, is it possible to get negative values?
Yeah.
Okay, so right off the bat, we're not normal.
I mean, couldn't it be like normally distributed between 0 and infinity? Like, so like,
Oh yeah, but that's not a normal distribution. Yeah, no, that's in fact what's called a truncated normal distribution. But that's not the normal distribution. That's a different distribution. If you take a distribution and you do something to it, you don't have that distribution anymore. So the delay in Q are literally not literally be normal. Okay, so right off the bat, there's a little bit of kind of an issue here. But they're going to be more. Okay, but this is what we're after. We're after, can we find a random sample for which the assumptions are reasonable enough? Now, what do your stats books say about a random sample that might not be normal? What do they kind of wave at it? They wave a magic elixir, which has a name. Remember, central limit theorem, does that ring a bell? Okay, what does the central limit theorem say? Basically, if you have a distribution, if you have a random sample, regardless of the underlying distribution, if you take enough samples, and if the mean exists, which again is not always the case, and if the variance exists, which again is not always the case, then in the long run, the sample mean is approximately normally distributed if you take enough samples. And there's a magic number that they always say. You remember how many samples? 30. Where did 30 come from? Did they tell you? I have no idea. As far as I can tell, there's some guy somewhere in his like a mad professor in his lab who says, "Yeah, 30 samples." Ah. You know, what value of alpha did you typically use? 0.05. Where did that come from? Probably the same guy in his. Yeah. So these are just kind of made up things. But they're actually reasonable rules of thumb. So we'll sort of accept that. And and just, I mean, if you're ever briefing something like this, then those give you sort of CYA types of things. So if somebody says, "Why did you take 30 samples?" You said, "Well, because, you know, my stats professor said 30 was, you know." Why did you take alpha 0.05? Well, it's my stats professor's fault. Blame him or her. But if you do something else, then I'm like, why did you only take 10 samples? Why wasn't it 30? Should have been 30. Okay, so as I said, there's a bifurcation on what we're dealing with, and that depends on a couple of factors. The two are terminating, and in the case of terminating, there's some natural or end event or condition. So if I'm analyzing, say, a combat scenario, there is typically, especially for a relatively constrained one, you know, you will begin with, say, a certain forces on both sides, and there will be some kind of ending condition, whatever it may be. And there are different ones. If I don't know if they still have you take wargaming types of stuff over in operations research, but you know, things like when one side reaches a certain percent of their forces, then you declare that they've lost. Or it may be something like, okay, when we achieve the objective by a certain time, then that's kind of a win. In those situations, again, you would typically start with some initial conditions, and then at the end you're in some other condition. Another situation for things that we've been looking at a little bit are if I'm modeling a facility that opens in the morning and closes in the late afternoon, let's say like a bank, one of our canonical examples for a multiple server queue. If I'm looking at that, then I start in the morning where I'm empty and idle. Remember, we started with nobody in the queue. And then say you close at 5, and then either let everybody out or or lock them in, depending on what the model does. So that's a semi. That's the quote. Bless you. That's the quotes in natural. In other words, if we have again, just think of a multiple server queue model, we could run it forever. But if we're modeling something where it kind of starts and stops, then we need to run it a little bit differently. So it's not embedded in the simulation itself, it's just the way that we run it. Now, a non-terminating situation is where there isn't a natural ending condition. So if I'm like a factory that's running 24/7, or even if I'm in a situation where I'm in a shop, and even if I close at the end of the day, the next day I kind of start up where I finished. Or a situation such as some of the inventory ones, where it's like the demands for the items are just going to kind of keep coming, and there's no, they always want more. So in a non-terminating case, you run it indefinitely. In something like a combat situation, if I ran it forever, eventually one side would kind of run out of forces. Just depending on how we're actually sort of modeling it. So in the non-terminating case, and it turns out that with a bunch of mathematics that we won't go into, you can basically show this, that there are really two possibilities, and you may have encountered both of those. Either the simulation is going to reach steady state, in which case we're going to have some measure. Our measure is going to be fluctuating about its value, or it blows up. Again, in our multiple server queue, if the arrival rate is too big, if the customers are coming too fast for us to handle, then what will happen to the model is eventually the queue will become arbitrarily large. In other words, the servers are always busy, the queue just gets bigger and bigger and bigger. And as you're, in models that I kind of made you write, it's likely that at some point you encountered that. And if you didn't, then you didn't, but you can at least imagine. Okay. So we're first going to talk about the terminating case, because in the terminating case, the way to analyze the terminating case is fairly easy, fairly straightforward. But the challenge there is actually kind of on the other end, and that is to figure out what the heck is being estimated. And now we need to kind of look at what it is, what the data that we're getting out are. And sometimes the stats, depending on who you have for stats, they kind of fuss about whether data is singular or plural. Data, strictly speaking, data is plural, of course. So datum is the singular. So it should always be data are, not data is.
Unless it's only commander data.
Yeah. Make that so. Okay. That's a good one. I'm going to steal that. Okay. So let's let's look at, again, our canonical example is delays in queue. The individual observations are not only, it fails both of the eyes. They're not independent, and they're not identically distributed. It should be clear that they're not identically distributed, but in case that it's not, let's just sort of do a little thought experiment on this. If we run our multiple server queue, beginning with no customers in the queue, what's the delay in the queue for the first customer? 0. Why? Because yeah, I mean, if now, all right. So now, great observation. Now let's envision a multiple server queue where there are no servers available at all. So what's that system going to behave like? Yeah, basically infinite queue. So given that we have at least one server, and we begin our model, with no customers in it, then the first guy is going to have a delay of 0. What about the second guy? Yeah, exactly. So if we have K servers, then the first K customers will always have 0 delay. We know that because they're always going to find an available server. What about the K plus first guy? Is the K plus first guy going to have a delay in queue of 0 for sure? No. Yeah, exactly. So it depends on a lot of complex things. It depends on whether or not somebody finished service first. So think what is the distribution, if you can kind of just sort of loosely characterize the distribution of the K plus first guy is 0 with probability that some of the first K guys finish their service, and it's going to be bigger than 0 for some quantity if nobody finished service before they arrived. And that's not the same as 0, so that's not. Now, what about the K plus first guy, K plus second, or the K plus third? And so now, what about the millionth customer? What's their delay in queue going to be like compared with the first few? It depends on a lot of complex things, and actually depends for the millionth customer. Strictly speaking, it depends on what happened in the system for the first 999,999 customers. And that's a fairly complex thing. So right off the bat, our observations are not identically distributed. They're also not independent. Now, is it obvious that they're not independent?
In this case, yes, but it might not be in a more complex situation.
Okay, well, let's do a little thought experiment. So we have a customer, and their delay in queue is sort of bigger than average. So we have some kind of average, let's say, and we have a customer whose delay in queue is bigger than average. What about the guy right after them? Is it more or less likely that their delay in queue will be bigger than average, or will it just be average? Yeah, intuitively, why?
They have to wait in line as long as the previous person.
Yeah, I mean, what is their delay? They're standing right behind some guy who spent a long time in line, and so where were they? They were in line right behind him. And so what's the only difference? The only difference is what the inter-arrival time that they had. So So yeah, I mean, maybe it's a little bit less, but if I tell you that customer 500 had a larger than average delay in queue, does that give you information about the 501st? You know, maybe not mathematically, but it does. If you wanted to place bets on whether the next guy was going to have a bigger or smaller delay in queue, you'd bet bigger. Whereas if you're flipping a coin, and I flip a coin 10 times and it comes up heads 10 times and it's a fair coin, what do you get? Does that tell you anything about what the 11th flip is going to be? It doesn't. That's independence. In other words, if I tell you what one observation is and it tells you nothing about what the next one is, that's, you know, loosely speaking, what independence is. Okay, so just to that was sort of our little thought experiment, but okay, what about it? Is that something which is real or not? Okay, so here's our, remember our entity server? That was the first model where we could actually estimate the delay in queue. And so what I'm going to do here is I'm going to basically, well, I have a little logger here, a property change listener that's going to take values, take property changes and just dump them into a CSV file. And so I'm going to look at all of the individual delays in queue. And it's going to dump them into a CSV file. I'll call it entity server. And I'm going to do it for delay in queue and time in system because I could do it for both of them. So if I run that, then what I get is, okay, this is what it just produced. It just produced a comma separated value for that delay in queue, time in system. And if you can kind of look carefully here, you notice that the first 1, 2, 3, 4, 5, 6, the first 8 or so delays in queue were 0, and then it started to go up, and then it's going to go up and down, and we get zeros and others. And in fact, when it comes to this, if our model, we're not, now I don't know whether this is going to be in steady state or not, but what I'm looking at here is I can compute the autocorrelation. Now, do you remember what autocorrelation is? Did they talk about that?
I think we have way more faith in our statistics.
We got regular correlation.
Regular, yeah. So, well, okay, so they didn't tell you about autocorrelation? Okay, so if I have a series of observations, then what autocorrelation, let's say autocorrelation of lag 1 is the correlation between the one guy, each observation and the one right after it. So you know what correlation is. So if I have a series of observations, then the autocorrelation is the correlation between the first and the second and the third and the fourth, etc. The lag 2 correlation is a correlation between 1 and 3, 2 and 4, 3 and 5, etc. So in other words, the lag n correlation is the correlation between each observation and the observation n in the future, you know, n after it. Does that make sense? So if you know what correlation is, then this should make sense. Maybe. So the question is, what is the autocorrelation of these? In other words, if I have a random sample, if I have independent observations, then what should the autocorrelation should be 0. You know, keeping in mind autocorrelation of 0 is not the same as uncorrelated, is not the same as independent, but independent implies a correlation of 0. You all know that. So a random sample, an IID sample, has an autocorrelation of 0 of all lags. That's a because if they're independent, the correlation is 0. If the autocorrelation is not 0, then that means they can't be independent. So, let's see. All right, so this is a graph of the autocorrelation of what I just generated. And let's try that again. Okay, so what, okay, so what this is a graph of this is the autocorrelation of the data that I just generated. And what the x-axis is the lag. In other words, this is the the correlation of lag 0, which is the correlation with itself, which is always 1. The next is the correlation of the lag 1. That's the correlation between one guy and the next guy, delay in queue. And that's the correlation between one guy and the guy 2 after them, etc. And as you can see, it actually, it's kind of an exponentially like thing, but what this shows is that the delays in queue are autocorrelated. In other words, we cannot apply our standard statistical tool to this raw data because they fail both of the eyes. The eyes do not have it. They are not independent, and they are not identically distributed. So what can...
Wouldn't they be, though, for observation k plus 1 through infinity? K is the number of servers? Because, is the issue just that you have all those 0 observations at the front, and then once you get through those, then at that point it would be?
No, actually, because you get 0 observations whenever the system empties, whenever the servers all become available, then the next, you're kind of back where you started. So you're always going to, in fact, if you never get 0 delays in queue, then your system is actually going to blow up.
On that graph, at that point where it could approach 0 have any significance, or?
Yes, it does. What that implies, let's see, do I still have, oops, I don't have it. I don't know why it does this. What that implies is that the correlation between, let's see, I can't tell. I think this is about 50 or so. Yes, what that implies is that as the lag gets bigger and bigger, the correlation between the delay in queue for one customer and the delay in queue for, say, the 100th customer after them is relatively small. And that actually is an important property. In other words, as you take the distance between respective customers, and as that gets large, then the correlation does go to 0. So that's an important observation. But it still doesn't help us because we're still down, like our successive observations are down here. So what that leads to is the question of what the heck, again, we're talking about the terminating case. And that sort of belies the autocorrelation issue as well. In other words, if we only have, say, 500 customers or so during the day, and the lag at which our autocorrelation becomes small enough so that we can ignore it is, say, 100 or 1,000, then we're still in a situation where all of our delays that we have observed are highly correlated. Okay, so what is it that we can estimate? Now, we have been computing, say, things like the average delay in queue for our system when we run it for a certain period of time. What does it mean, though, when you take the average of observations that are not identically distributed? Each observation has a different mean. The mean of our first K customers is going to be 0. We know that. The mean of K plus first customer is going to be a little bit bigger than 0. And the mean of our K plus nth customer is going to be whatever the heck it is. So again, back to in the stats context, where we have a random sample, they're identically distributed, so they all have the same mean. And so when we take our sample mean, we're estimating that one thing. If I take a bunch of samples that have different means, then what the heck am I estimating? Okay, so we've already established that our raw simulation data is, and here, is or are not typically IID. Each has a different mean, and they're not independent. You know, we've sort of at least done an intuitive example of that, done a statistical example of that. So here's what we've been estimating so far. And so what we can do in the terminating case is try to find out information about this average. And what is it that we're trying to estimate? Well, what we get when we take the mean, the average of our delays in queue for our model, is that we get one observation of the expected average delay in queue for the first n customers. Now, notice there are two modifiers, the expected average delay. In other words, if we have n customers, and each of them has a different expected delay in queue, remember the first K have an expected delay in queue of 0, and what we can do is we can estimate the expected average delay in queue for the first n customers. That's basically what we can do. And so with that, and operationalizing this is the easiest of all, which we will do next time. I mean, we can do it theoretically here. But if we run our model once and take the average of our delays in queue for that one run, we're going to say that gives us one observation. But what if we run another replication starting with the same initial conditions and under the same ending conditions? So if we run our bank starting for, let's say, 8 hours, starting with no customers, and after 8 hours we estimate the average delay in queue for that. If we do that independently again under identical conditions, we now have an independent replication of this experiment. And if we've done it under identical starting conditions and identical parameters, they are also independent, they're identically distributed. And so after all that, if we run capital N replications, each of which is computing the mean, the average delay in queue of that, then now we're back to our random sample. These are independent and identically distributed. And now we can apply our usual, so we take the mean of the means, because they're independent, we can now apply our estimator for the variance. And that's what goes off. If I have autocorrelation, this equation for the estimator of the variance is incorrect. It is biased. And it's biased typically in the wrong direction. If I have positive autocorrelation and I just blindly apply the formula for the variance, then what I get is I get an estimate of the variance that's much lower than it has any right to be. So now that I have this random sample, I can apply my estimate of the variance of this. And now, sort of the mean of the means, plus or minus our usual suspects here, which is the standard deviation of these means over the square root of the number of replications that I've performed, and a t-distribution with n-1 degrees of freedom, and the 1 minus alpha over 2 business. We now have a legitimate, approximate 100% 1 minus alpha confidence interval for the expected average delay in queue of the first n customers. And furthermore, it turns out that we're also in relatively good shape in terms of our normality assumption, because even though the delays in the queue themselves are definitely not normal, if we take the average, if we take the average even of autocorrelated values, there's a central limit theorem for that. And so these averages are arguably approximately normally distributed. So our normality assumption is a reasonable one in that case. Okay, so all this is fine and good, and so now I'm sure you're all wondering, how the heck do I do this? And all that will be revealed tomorrow.